Welcome to Physics 360. This is an online lecture about Chapter 1, Section 11 and 12. This is basically all about coordinate systems. Alright, so the first coordinate system is polar coordinates. And we'll start by defining our Cartesian axis of x and y. And z is out of the plane. And then we have some point we're going to call P. And we want to define that with this vector called r. And that r makes an angle theta with the x-axis. And this is what is called polar coordinates. And there's this unit vector that points in the direction of r, but only has a magnitude of 1. So we can figure out the x-coordinate of what point P is, the y-coordinate of point P, and then actually the magnitude of r, we can use this expression, and then angle theta can be done this way. But we want to represent this in polar coordinates, and the way we do this is this, or the vector r is represented by the magnitude r times the unit vector of r. And so by definition, a velocity is the derivative of our position vector with respect to time. So I'm going to do that. I have to take the derivative of our polar position vector. And if I do that, I apply the product rule, and I get the derivative of the magnitude of r times the unit vector of r plus the derivative plus r times the magnitude of the derivative of r. Well, the derivative of r with respect to time is easy. It's r dot, or that's the velocity, or the rate of change of the magnitude of our radial vector with respect to time. I should say the magnitude of that. And that always points in the r hat direction. But what we have to figure out is how the unit vector changes in time. And that's a little more challenging. So to do that, I'm going to write out our unit vector. It points that way. And then there's another unit vector called theta hat, and it's always 90 degrees to r. And what we're going to do is we're going to rotate that system some displacement of delta theta. And then what we get is the change in r is the change in r hat is the blue arrow, and the change in phi hat is the little black arrow. And we get those changes. So what I'm going to do is I'm going to define my change in r as this by using the representation of an arc length. We're assuming that r hat is not changing its length and that delta theta is small. So what happens is we get the change in r times the radius of the vector. That's what's called the arc length. The change in the angle times the radius of the angle. And as you can see, this little blue arrow points in the direction of theta hat. So it points in the direction of theta hat. And I can do the same thing. So what I can do is the magnitude of the unit vector is 1. So I can write this as the change in theta times r hat. So the change in r, or the change in, I should say, the unit vector r is equal to the change in theta times theta hat. And I can do the same thing for the change in the unit vector of theta is going to be it also doing the same thing. And you'll notice it points in the opposite direction of r hat, so I've got this negative sign here. And this is the magnitude of theta hat. But that's going to be 1, and so I can write my change in my unit vector theta hat in this fashion. Okay, so what we're going to do is use these to help us to get the derivative of our unit vector. And so by definition, my change in r divided by my change in time would be equivalent to this. And what I'm going to do is take the limit as t goes to 0, and if I do that, what happens is I get my change in r hat vector with respect to time is equal to my change in theta with respect to time, and times the theta hat vector. And basically the change in theta with respect to time is called theta dot, or the velocity, the radial velocity of our change. So if I use these ideas, I can plug them back into our expression for the velocity of a particle in polar coordinates, and I get this expression. So what I did is I took this and replaced it with this, and so this is the change in velocity. I can velocity pointing along the radial direction, and a velocity that changes in the angular direction, or in the theta hat direction, which is the angle direction, and I get the velocity like that. And I can do the same thing for the theta hat unit vector, and basically the derivative of theta hat is equal to theta dot times r hat. And I've gotten rid of the minus sign because the minus sign just denotes direction, and direction is carried along with the unit vector in this case. So what we have now is the velocity of an object using polar coordinates, and now we also want to get the acceleration. So to do that, I'm going to bring back the techniques. I figure out how to find the change in the unit vectors of the change in r hat with respect to time, and the change in theta hat with respect to time, because I'm going to have to find the acceleration, and the acceleration is the derivative of the velocity with respect to time. And so to do that, I have to take this derivative and then apply this massive chain rule. And if you see, I've got my derivative with respect to time for r hat, and a derivative with respect to time for theta hat, and then I have the derivative here of r and theta dot. And what we're going to do is take these definitions for the derivatives of the unit vectors and plug them in. And if we do that, we get this expression. This right here is the derivative of that. And then you see I've got several vectors that have the same unit vectors, several components. I've got a theta hat component here, I got a theta hat component here, I got an r hat component, and I got an r hat component there. And if I bring them together, this is the acceleration vector in polar coordinates. So our next coordinate system is cylindrical coordinates. And what we're going to do there is use the Cartesian system, our x and our y and our z here, and we're going to have another point P. But the way I define point P is I bring out this vector called rho. Rho is parallel to the xy plane and comes out to point P from the z-axis. So what that's going to do is project itself down on the xy axis, and you determine that projection through this angle called phi. And so then I get my unit vectors, where I get a rho hat, I get a phi hat, and then now I get a z hat. Okay, and that's points parallel to the z direction, and phi hat points parallel or perpendicular to the rho direction. And we're going to do a similar strategy that we did in polar coordinates, but we're going to use cylindrical coordinates to do this. So cylindrical coordinates has a rho component, a phi component, and a z component. And so I can get my x component by doing this, my y component by doing this in Cartesian, and I can get rho is equivalent to that, and the angle is equivalent to that. But then I have to use my z. Well, z in Cartesian coordinates is the same z in cylindrical coordinates. So you get those values. So the way you represent a position vector in cylindrical coordinates is you've got a component that points in the direction of phi and a component that points in the direction of z. And then if you wanted to do the velocity of this particle in cylindrical coordinates, you have to take the derivative position vector. And that's exactly what we're going to do. And if you do that, you see I got a derivative of a unit vector called phi, a derivative of the unit vector of rho, and a derivative of the unit vector for z. So what we're going to do is start rho out first, and the unit vector of rho is perpendicular to the unit vector of phi, and then we're going to rotate them again through some angle called delta phi, and then the difference in these two are going to be my change in my unit vectors, just like we did before. And so I can calculate my change in my unit vector for rho is equal to this expression, and since rho hat is a unit vector, it has a magnitude of 1, I can represent it with this expression. And I can do the same thing for the change in the unit vector phi, and I get this expression. Again, the change in unit vector of phi points parallel to rho, but it points in the opposite direction, so that's why we have the minus sign. So I'm going to do the same thing we did before. I'm going to try to calculate my change in the unit vector of rho versus my change in time, and take the limit of time go to 0. And if I do that, this expression goes to this. So this gives me a way of calculating my change in my unit vector for rho with respect to time, and that should be phi hat times the unit vector in the phi direction. So I can do a similar thing for phi, and so I get this expression. And then what we have to do is calculate velocity. So let's make our substitutions up above. What we're going to get is that. So I can substitute in my definition for the derivative of the position vector, or the rho position vector, but I have to figure out what my change in my z vector is. Well, it's actually 0 because z never changes in this rotation because we're rotating it around z and not rotating around the x Cartesian axis or the y Cartesian axis. So that goes to 0. So what we get for our velocity of a particle using cylindrical coordinates is this expression. And again, I could calculate the acceleration if I took the derivative of my velocity in cylindrical coordinates and do a similar strategy that we've done before to figure out what that is, but I'm going to leave that up to you. I'm going to move on to a new coordinate system. I'm going to move on to cylindrical coordinates. Sorry, I'm going to move on to spherical coordinates. And again, we have the same Cartesian reference. In this case, my point P is met with a vector r that goes from the origin out, and it is moved away from the z-axis by some angle theta, and it makes a projection in the xy plane again at some angle phi, and it's got a unit vector that points in the radial direction, one that points in the phi direction, which is 90 degrees to the radial direction, and one that points in the theta direction, which again is 90 degrees to both r and phi hat. So I get, in spherical coordinates, I get an r, a theta, and a phi. And this would be my z component in this case. And then I have to have the projection in the xy plane, which is r sine theta. And then I use that as the magnitude to figure out the projection for x. And I get this definition for x and this definition for y. And of course, this is my definition for r, and this would be my definition for theta. Oh, sorry, phi. My definition for theta would be this. And so, if you define this radial vector in spherical coordinates, it's defined this way as some magnitude of that vector times the unit vector of r. And so we have to find its velocity. To do that, I have to take its derivative, and I get this expression. It's very similar to what we did in polar coordinates. But the problem is how does r hat change in time? Well, to do that, I want to calculate the magnitude of r hat. And to do that, I apply this definition. This would be in Cartesian coordinates. It just so happens it's easier to do this in Cartesian coordinates than in cylindrical or in spherical coordinates. And so I get this expression. That's my unit vector. So I have to see how that's changing in time. So I have to take its derivative. And if I do that, I get this expression. So what you'll see is I have in each coordinate, I have a term for theta dot and a term for phi dot. So what I'm going to do is group them together. I'm going to group all the terms that have phi's in them in one spot, and all the terms that have theta dots in it one spot. And for the phi dots, there's also seems to be a sine theta component in each one of those. And you see I have this vector right here that ends up multiplied times my theta dot, and this vector multiplied by my phi dot times sine theta. Alright, so what we're going to do is look on how r and theta change. R hat and theta hat change. So there's my theta, and there's my derivative that I've calculated already. And there's my simplification that we did to factor out all the theta dots and phi dots. And r hat points in the direction of r, and theta hat always points 90 degrees to r in the plane of r. And you'll notice if I project down to the axis, I get these angles that show up. So the angle between my projection for theta hat and on this blue dotted line is going to be 90 minus theta. So what I'm going to do is find these two projections. So I'm going to draw a bigger picture here for you so you can see what they are. And that's phi hat, that's theta hat is the green arrow, and there's the angle between the blue dotted line and the green arrow is 90 minus theta. So this would be my projection in the xy plane, and this would be my projection on the z-axis. So using some trigonometry, they conform to this. Using the double angle formula, they conform to this. So the component of theta hat on the z-axis is sine theta. And remember, theta hat has the magnitude of 1. Now I got to work on the projection in the xy plane. Well, the projection is cosine theta, and I have this new angle of phi, so I create my x component would be cosine theta times cosine phi, and my y projection would be cosine theta times sine of phi. And so that gives me the coordinates. Now, if you look at the vector up here, my x coordinate is cosine theta, cosine phi. That's exactly what I have here for my x coordinate. I have my y coordinate is sine theta, cosine theta, sine phi, and that's what I have right here for my y coordinate, my y projection. And my z coordinate is minus sine theta. Well, here's my z projection. It's sine theta, but the minus is because this component points down here, and that would be the minus direction. So this term right here in spherical coordinates is theta hat. So I put that in there. Now let's do the similar strategy for phi, or phi hat. So if you think about this, phi, which is this green arrow, has to be perpendicular to both r and theta. So it's just going to have no coordinate on the z-axis because it's going to lie in the xy plane below. So we need to figure out its angle. So that's phi, and so that has to be phi. So if I figure out its y component would be cosine phi, and its sine component would be sine phi. And that is actually pointing in the negative x direction. So if I come up here, I have negative phi, negative sine phi, cosine phi for the y. And so this term right here comes out to be phi hat. So my velocity in the spherical coordinates would be this, and now let's multiply through by the r and group terms together that have the same unit vectors. So I get this velocity in spherical coordinates of an object with a position vector var at some point p, and so it would have that velocity if that velocity is changing in time. Okay, so this finishes our spherical coordinates and finishes the three coordinates you should be familiar with. I'll talk to you later.